Hello everyone. So today we'll be looking at the fourth experiment, which is called behavior of a second order system. That is, till now we have been studying about the first order system, but now we will be studying about second order system. Since we are studying about second order system, that is the order of the system has increased. How do we increase the order of a system? We increase the order of a system by integrating it. That is, apply an integrator or 1 by s if we are considering in Laplace domain. So since the first order system related to velocity, in the second order system, since we'll be integrating the velocity, it will relate to our position. So second order system is actually our position control system. Now, earlier we had our input R, we had our, uh, from here we have our controller KC, then we have KP, which is the plant. Now we'll have another factor called Ki. This Ki is the integrator again, and we'll have output C. This output C is actually the position output, and we have a unity negative feedback. So this is now our signal flow diagram of the system that we'll be looking into. Now you must have learned a lot of things in theory, but I'll discuss some things here as well. uh, if you look at the graph, what can happen is, depending upon different values of damping and other things, uh, if your input is a square wave, that is, input is a step, you can have different types of output. For example, your output might be like this. Sorry, let's change the color for easy understanding. This is our input, and output might be like this, or output might be like this, or output might be just like this, or output might be like this. That is a sinusoid. So these four kinds of outputs are there. So this system over here, where there is an offset from the steady state, we call this system as a underdamped system. You already have learned it in theory. I'm just recapping it. This system is critically damped. This system is overdamped, and this system is undamped. So what happens is, obviously we undamped system is oscillatory, and we actually rarely want undamped system. We generally do not want undamped system. What do we want? We either want underdamped system, critically damped system, or overdamped system. So what are the benefits? Before we look into the where we want which system, let us look at the benefits at first. The benefit of underdamped system is it is very quick. You can see the time constant of the underdamped system is very low. It reaches the peak at a very fast time. So the advantage of underdamped system is it is very quick, but disadvantage is it gives an overshoot. That is, before reaching a steady state, it will show a jerking motion. When we come to critically damped system, when we come to overdamped system, we can see overdamped system is very slow. That is, it reaches the steady state at a very late time. But overdamped system, there is no jerking involved, so overdamped system is very stable. And critically damped system is something in between the underdamped system and overdamped system. So this is the quickest system possible without giving any overshoot. So technically, it may seem like critically damped system is our best for any type of operation, because this is a balance between the speed of underdamped system and high stability of overdamped system. But that might not be the case. It actually very readily depends on the kind of operations we are using. For example, if we are suppose we are developing a fan. What we are concerned in a fan is that it reaches the highest speed at the quickest possible time. If the overshoot is high, that is, if there is a jerking at the beginning, we don't actually care. We want the high speed to be achieved as fast as possible. In that case, in case of fan, we will actually be using underdamped system. Again, is the case same if you use a crane in construction site? In case of crane, if there is a delay in work, that's not a problem, but stability is a big issue in crane. Suppose if there is a jerking in crane, crane always lifts very heavy stuff. If there is a jerking, then what can happen is this stuff can get detached and can hit anyone and can cause an accident, can break the stuff and all sorts of things. So in case of crane, we are actually preferring the overdam system. Similarly, is the case of lift. We want safety first and we want speed later. So lift would be a perfect example of critically damped system because we actually want some kind of speed in our lift as well, and stability is also issue. So we, in case of lift, we are more inclined towards designing a critically damped system. In case of crane, we are more inclined towards over damped system because of its higher stability. In case of fan, we want under damped system more because we want faster response. So what will be the system that we design? It will depend on a lot, depend on its specific area of operation. Now, before we move into what this the factors that will define whether a system is under damped, over damped, or critically damped, we just look at some basic definitions associated with our operation. So let us just for sake of understanding, let us look at an underdamped system. So this is an underdamped system. So this is the highest peak. The time it takes to reach the first peak is called TP, or peak time. The time it takes to reach the first peak is TP, or peak time. Now, in this system, let us suppose that this is our input. That is, the blue line over here is our input and the black is output. So time it is needed to reach the peak is peak time, and the time at which the output crosses the input for the first time is called the rise time, TR. This is the rise time. And there is another phenomena called overshoot. Suppose this magnitude over here, the magnitude of the greatest peak, we are considering it at M1, and the magnitude of steady state we are considering M2, then overshoot is equal to M1 minus M2 divided by M2. And generally overshoot is expressed as percentage, so percent overshoot is equal to this into 100%. One thing is to be noted, and we should be very careful about it, that this M1 is not the value of this peak. Rather, it's the value of the difference between the lowest point and the peak. And again, M2 is not the value of steady state. Rather, it's the difference between the lowest point and steady state. For example, if lowest point is 0, this peak is 3, this peak is 2, then M1 is equal to 3, M2 is equal to 2, no problem. But if the lowest point is not 0, but it's minus 2, then M1 becomes minus 2, the difference between minus 2 and 3, that is 5, and M2 becomes difference between minus 2 and 2, 4. So overshoot is dependent on this distance and not actually the peak value. So we have learned about overshoot, we have learned about rise time, and we have learned about peak time. There is another time involved which is called settling time. Settling time has different type of definition, 1% definition, 5% definition. So just let us take a 2% definition. This is our steady state output. We consider 2% plus minus the steady state output. So we'll get a range over here, that is plus minus 2% of steady state output. Now the time at which the output reaches this range, and after that time the output never goes out of this range, that time is settling time. For example, here in this case, in this position, the output reaches this range, But as you can see, suppose let's change the color. In this position, output reaches the range, but in this position, it goes out of the range. So this is not our settling time. Again, in this position, it reaches the range. Here it goes out. Here it reaches. Here it goes out. In this case, in this place, the output reaches the range and output never goes out of it. So this time over here is called settling time. So we have learned about rise time, we have learned about peak time, and settling time. We have learned about overshoot. Now, based on this, there are certain phenomena that will be, or certain definitions that we'll be learning. The first definition is damping factor. Damping factor, also defined as zeta. Damping factor zeta is equal to root over 1 divided by 1 plus pi divided by ln OS square. Now it is to be noted that this is overshoot and not percent overshoot. So this 100% will not be there. So this is the damping factor zeta. And damping factor has a great role to play because if zeta is equal to 0, the system is underdamped. If theta is equal to 1, critically damped. If zeta is less than 1, sorry, if zeta is equal to 0, undamped, not underdamped. If zeta is equal to 0, we get undamped. Zeta is less than 1, we get underdamped. Zeta is greater than 1, we get overdamped. So based on the value of zeta, we understand whether a system is undamped, underdamped, critically damped, or overdamped. So zeta is very important in that way. There is another phenomena which we'll need to learn which is damping frequency. Let's write here. Damping frequency is equal to 2 pi fd. Damping frequency is defined as omega d. Omega d is equal to 2 pi fd. So we know f is equal to 1 by t, 2 pi by td. Td is the damping period. So generally Td is this period from starting to this point. The first trough, this is Td, but we don't, there is no definite term as Td or the damping period or the period of oscillation. So what we do is the first peak is half of the total time period. So what we write, what do we use? We use Td is equal to 2 Tp. 2 Tp. So if we modify it, we get omega d is equal to pi by Tp. But 2 and 2 get cancelled. So omega d is equal to pi by Tp. This is our damping period. Damping period is a period of oscillation of a damped system. Underdamped system. Period of oscillation of an underdamped system is damping period. And the phenomena is called natural frequency. Natural frequency omega n is defined as omega d divided by root over 1 minus zeta square. Natural frequency is the frequency at which an undamped system operates. So we know undamped system is an oscillatory system as I have shown earlier. So the frequency at which that undamped system will operate is called the natural frequency. Now, damping factor, this is the basic definition of zeta, basic definition of omega n, and basic definition of omega d, which are dependent on the properties of the graph. But in our system, we do not have a graph. We have a controller with a gain Kc, we have a plant with a gain Kp, and we have an integrator with a gain Ki. So we cannot control how the graph will look like. We can control the shape of the graph using Kc, Kp, and Ki. So there must be a way, there is supposed to be a way using which we can control this damping factor zeta, this natural frequency omega n, and this damping frequency omega d using this Kc, Kp, and Ki. So there are some equations involved. The equations are, uh, let us just get rid of this extra things. Let us get this is there and this is there. Everything except we have gotten rid of. So the equations that we'll be using is uh, our zeta is equal to root over omega c divided by 4 Kc, Kp, Ki. Now, what is the omega c? Omega c is we have found out in experiment 2. It is break frequency. Kc is the controller gain, Kp is the plant gain, and Ki is the integrator gain. We have no control over Ki and Kp. We have only control over Kc. Omega c is also plant dependent, so we don't have control over that. So what we can do is we have control over Kc. So if we increase the Kc, the value of zeta will decrease. If we decrease the Kc, the value of zeta will increase. That is, increase of Kc. If Kc is increased, zeta will be decreased. The system would be underdamped. If Kc is decreased, zeta would increase. The system will become critically damped to overdamped. So based on by controlling Kc, uh, we can control actually the overshoot or the damping factor. Since the overshoot is directly related to zeta, we can control the overshoot by controlling Kc. And we will be seeing in the experiment that if we increase Kc, overshoot increases. Now, that is the definition of Kc. In the similar way, we can find that omega d or the damping frequency is equal to root over Kp, Kc, Ki, Kp, Kc, Ki, omega c, which is the break frequency, 1 minus zeta square. And this is the definition of omega c, omega d, and omega n would be equal to root over Kp, Kc, Ki, omega c. So by using these formulas, we can determine omega n, omega d, and zeta. And what we can do is, using these plant parameters, we can actually define the overshoot that it will have, and the frequency response. That is, how fast the system will operate and the overshoot that it will have. Now, uh, okay, now let us just look into it. Or for example, see, in case of omega d, we get omega d will increase if Kc will increases. Now we know Tr rise time is proportional to 1 by omega d. Rise time is proportional to 1 by omega d. If that is the case, then as omega d increase, rise time decreases. That is, the speed increases. Since time decreases, the speed increases. So increasing Kc will decrease the zeta, will decrease the rise time. That is, improving Kc will improve the speed performance, but the overshoot would be higher. Decreasing Kc will decrease or would make the speed performance worse, but overshoot would be less. So the effect of Kc has a trade-off. If you want if you want faster system, will increase the Kc, but at that case overshoot will also increase. If you want slower system, will decrease the Kc, but at that case uh, overshoot would be overshoot would decrease. So either we can have a fast system with greater overshoot, or we can have a slow system with smaller overshoot. We cannot have the best of both worlds, just considering Kc into operation. So we have talked perhaps a lot about the theoretical aspects of it. Now let us see what do we need to do in case of our experiment. Let's move into our experimentation. Now, before we move into our experimentation, let us just go to the data sheet at first. What data do we need? So data sheet says that we'll put Kc is equal to 1.5, then we'll measure the overshoot, we'll measure zeta, or from the overshoot, from the equation we'll measure zeta, we'll measure Tp, first peak time, we'll measure omega d and omega n. These values are measured from the actual equation, that is from these equations, and this equation. Using this equation, we'll be measuring it. So that will be the pure values. And in the second table, again we have Kc 1.5. We know Kp and Ki from and omega c from first experiment. So from this, we'll determine zeta from this expression. From this expression, we'll be determining zeta. That is, we'll be determining the zeta from Planck constant, or different plant controls, and then from that zeta we'll be determining omega n from this equation over here. So this equation and these equations, these are our practical equations. That is because these equations depend on our practical life controllers, that is real life controllers, Kp, Kc and Ki. And these equations inside the box, these are theoretical equations. So what we do in this experiment is we find the theoretical in the first table, we find the practical equations in the second table, and we compare these two. Now, let us look how we can do that. Firstly, we have to load CA06P07. So file load CA06P07. Now, if you look into it, signal is step, level is 30%, offset 0%, wait 10 milliseconds. So signal is step, 30%, 0%, 10 milliseconds, everything is there. So we do not need drive, so we switch the drive off. We just need the input and output of it. The input and output. Okay. Now inputs and outputs are there. So what do? We freeze the system. See, Kc is equal to is placed 1.5, and these values are placed according to my initial. I'm placing these values same for all the experiments, and you'll also keep these values same for all your experiments, which will depend on your student ID, as I have discussed in experiment 1. Now, the first thing to do is freeze it. After freezing it, I'll have to determine, let's look at the data table first. I'll have to determine the overshoot. So how can we determine overshoot? We actually go here. We keep the timer on. A is kept at here, the peak, and B is kept at here, the trough, or the negative most point. So what do we get? What is our value of M1? The value of M1 is 2.750 plus 1.5. So let's write here, M1 is equal to 2.75 plus 1.5 is equal to, excuse me while I reach to the calculator, 1.5 plus 2.75, this is equal to 4.25. M2 over here is, let's look at it again. This is our steady state value, which matches with the input as well. So let us take A and place it here. This is a steady state value. So this is 1.5. So M2 is equal to 1.5 plus 1.5, that is M2 is equal to 3. From the value of M1 and M2, we can find overshoot, which is 4.25 minus 1.5. Sorry, 4.25 minus 3 divided by 3. That is, for overshoot is 40. Percent overshoot is 41.66%. So, and overshoot is equal to 0.4166. So this is our overshoot. Now putting this overshoot in this equation, we can determine zeta. So how can we determine zeta? We put it root over 1 divided by 1 plus bracket starts pi divided by ln of 0.4166, and we end the square end the bracket and give a square. So by calculation we find zeta is equal to 0.268. Zeta is 0.268. So from this data table we have found overshoot and zeta. The third thing is TP. Let us look at it. Let us select time and click here. The time of reaching first peak 400 millisecond. So we can write TP is equal to 400 millisecond. And the fourth thing that you'll see is after TP we have omega D and omega N. Now omega D we can find from this expression. So omega D is equal to pi by 0.4 is equal to 7.85 radian, and omega n would be omega d divided by 1 minus zeta root over 1 minus zeta square. So omega d divided by root over 1 minus 0.268 square, so 8.15. Omega n is equal to 8.15. So the first table is fulfilled for me, and now we'll look into the second table. You'll not be requiring any experimental data to fill out the second table. You know Kc is equal to 1.5, Kc is equal to, in my case, 0.92, it will be different in your case. Ki is equal to 10.31 in my case, it will be different in your case. So you'll be fine. And omega c we have found in experiment 2. So we get the value of Kp and Ki from experiment 1, omega c from experiment 2. Using these values, we can find zeta. We can use this formula to find zeta, omega c divided by 4 Kc Kp Ki. And since I don't know the omega c or the break frequency at this moment, I cannot calculate it. You can calculate this from your data sheet of experiment 2 or the report of experiment 2. Then after we have calculated zeta, we can calculate omega n from this expression. So after calculating this, we'll be comparing with this zeta and this omega n and see whether these things are working. Now that's all for this experiment. Now let us look at one thing. I said that this is a position control system. So how the position control is actually working. If you look at the top right corner of your window, you'll see how the position control is working. You'll see at one, since this is a step response, at one direction it is being fixed at one particular position, and when the direction is reversed, it's also being fixed to that particular another particular position. So you'll see that it oscillates between two positions. And how would you know that it's oscillating between two fixed positions? You just look at the pattern of the ring associated with it. If you just look at the pattern of the ring, you'll see that it goes from one fixed position to other fixed position and back to the first fixed position. So this is how the position control system is working. In your report, you'll change in this stuff and do the calculations as I have shown in experiment, and you'll be answering the questions. That's all for this experiment. In the next experiment, we'll look at how we can get past this disadvantage of uh, this trade-off of Kc. Let us look at the trade-off of Kc for once. For example, here Kc is 1.5. If we decrease Kc, what you should observe is the system will become slow, but the the overshoot will be less. So let's decrease Kc. See, the overshoot is decreased by a great amount, but the system is becoming very slow. If we increase the Kc, the system will become very fast, but the overshoot will keep on increasing. The more we increase Kc, the more the overshoot will increase and the faster the system will get. So that is that is the trade-off. That is, using only this KC, we cannot get both fast response and stable response. We can either get fast response or get stable response. That is, there is a trade-off. In the next experiment, we'll try to explore the trade-off and we'll try to find a solution to it. That's all for this experiment. Thank you.